Multinomial logistic regression. Logistic regression is a classification algorithm. It is intended for datasets that have numerical input variables and a categorical target variable that has two values or classes. Problems of this type are referred to as binary classification problems. Logistic regression is designed for two-class problems, modeling the target using a binomial probabilistic distribution function. The class labels are mapped to 1 for the positive class or outcome and 0 for the negative class or outcome. The fit model predicts the probability that an example belongs to class 1. By default, logistic regression cannot be used for classification tasks that have more than two class labels. Hence, a multi-class classification is required. In a multi-class classification model, instead of the binary classification, it requires modification to support multi-class classification problems. One popular approach for adapting logistic regression to multi-class classification problems is to split the multi-class classification problems into multiple binary classification problems and fit a standard logistic regression model on each subproblem. Techniques of this type could include one versus rest and one versus one wrapper models. Now you can think of it in this way. You can think of it as an if-else if ladder where binary classification is performed at every if condition. It checks if a particular if condition matches with the classification. If it does not, it goes to the next condition, and so on and so forth. An alternative approach involves changing the logistic regression model to support the prediction of multi-class labels directly, specifically to predict the probability that an input example belongs to each known class label. The probability distribution that defines multiple class probabilities is called multinomial probability distribution. A logistic regression model that is adapted to learn and predict a multinomial probability distribution is referred to as multinomial logistic regression. Similarly, we might refer to default or standard logistic regression as binomial logistic regression. In binomial logistic regression, standard logistic regressions are performed where prediction of binomial probabilities, that is, categorization into two distinct classes for each input example, is performed. In multinomial logistic regression, modification of the binomial logistic regression is performed, which predicts a multinomial probability for each input example, that is, classification into more than two classes. Changing logistic regression from binomial to multinomial probability requires a change to the loss function used to train the model and a change to the output from single probability value to one probability for each class label. Let us now look at the application of multinomial logistic regression on text classification. Performing multinomial logistic regression We import the necessary libraries and packages. We load the data. We perform cross-validation for the hyperparameter tuning. We first see the hyperparameters the model currently uses. It currently uses 14 parameters. It is C, class weight, dual, fit intercept, intercept scaling, and so on. We will tune 5 of these parameters. The first one would be C, which is the inverse regularization strength. Smaller values specify stronger regularization. Multiclass. We will choose multinomial because this is a multi-class problem. Solver is an algorithm to use the optimization problem. For multi-class problems, only Newton CG, SAG, and Saga and LBFGS handle multinomial losses. You do not need to break your head into what these short forms are used for. Are for class weights are the weights associated with the classes. Penalty is used to specify the norm used in the penalization. Only 12 such penalties are used. For randomized search cross-validation, we first need to define the grid. For the value of C, we have the grid starting at point 1 and stopping at 1, hence we have 10 grids. For multi-class, we have multinomial. Solver, we have Newton CG, SAG, SAGA, and LBFGS. These are the respective solvers. The class weights, we have it as balanced or none. Penalties, we have 12 penalties. We then perform the random search, setting 3 folds for each of the 50 candidates, totaling 150 fits. We can find the best hyperparameter resulting from the random search, which gives us a mean accuracy of the model with these hyperparameters, which is 95.66%. After that, we can perform an exhaustive search centered in those values. We now fit 3 folds for each of the 10 candidates, totaling 30 fits. And with this, the best hyperparameter turns out to be with an accuracy of 96.85%. We fit the model and test its performance. For training the data, the training accuracy is found to be 98.14%. The test accuracy is found to be 94.01%. From the classification report, we can find that the average value of precision is 94%, recall is 94%, effort score is also 94%. We then have the confusion matrix where we find that there are 77 articles on business, 47 on entertainment, 64 on politics, 71 on sports, and 55 on technology.